I'm watching it because I need to mute it immediately. I don't want
Yeah,
my old blargada blargada.
yeah. I
Oh,
made the
there it
mistake
goes.
of using desktop audio and then accidentally trying to listen to my stream at the same time, and oh
Oh
lord.
yeah, yeah. Uh, Binomial Theorem is pretty fun. I remember when it finally clicked for me. I was like, oh, that's kind of cute. Kind of cute.
Good. And that's the way you should respond to a mathematical theorem like that.
Yeah, it's cute. I think it's one of the cuter ones.
Yeah, definitely.
Uh, so has your live lecture attendance gone down?
It has.
Yeah, same. Samesies.
Well, don't tell the students this, but
Well, aren't we broadcasting to the students right now?
maybe. Um,
Maybe we shouldn't keep any of our secrets. All right, don't tell the students what.
well, I mean, obviously, I'm thinking of maybe some kind of extra credit possibilities for students who they don't have to watch the lecture live, but at least watch it. I'm thinking of
Eventually.
embedding little, what you call it, Easter eggs in the
Mm.
lecture. Like if you text 3030 to Joe Biden.
Oh no. Yeah, we didn't debate something. We're gonna start with a debate. I have to
Well,
take
what
that
do we
in
actually
our
disagree about?
I see. I don't know what we actually disagree with, but I could try to argue that Star Wars is better than Star Trek.
I don't think there's a strong argument, especially if you're
You,
weighed down by the last three mainline movies.
oh, that's true. That's
Now,
true.
if
But
you
what
wanted
about
to
sort
make
of?
the argument that the original three Star Wars were comparable to, say, the original series Star Trek, I would say you have a case.
Oh, really? See,
Yeah, I
that's
mean, the
no.
original
You're
series
thinking.
Star
You
Trek was
mean
kind of hokey.
Captain Kirk? You mean Captain Kirk Star Trek?
Yes, of course, of course.
Okay. What about Next Generation versus the original Star Wars movies?
Next gen versus original three.
Yeah.
I mean, it's hard. It's a hard call. I
Hard
think
call.
next. I mean,
Well, what do
it,
you think the
it depends on
original
the
Star Trek?
metric, right?
Yeah. Do you think that the original Star Trek is better than the Next Generation? Like, which one of those
No,
two
no.
is better?
Next gen is clearly uh, Gene Roddenberry's like optimal show. It was the thing that even he basically said like this was the one that I wanted to make in the '60s but couldn't. So
I see. I see. So is that your pinnacle? Is that your Star Trek
yeah, I
pinnacle?
feel like next gen is definitely the one that if you have to judge Trek, you have to judge it by next gen.
I see.
Unless
I
of
see.
course you're one of those DS9 fanatics or something.
Oh yeah, that's a that's a special class of human. But
Yeah,
Star Wars versus Next Generation.
I think.
Mm,
Well, if you're looking for an optimistic view of a potential future and like good sci-fi stuff, then Star Trek wins by a landslide. But if you're looking for cowboy in space, right, like Han Solo style World War II dogfighting stuff, then Star Wars wins.
yeah, yeah, it's
I
true.
can't
There's
believe I'm
just
saying Star Wars wins anything, especially given the hate that I've poured down on it in recent years.
yeah. Well, it's not undeserving. I haven't even watched the what is it, episode 9? I haven't seen that yet.
The rise of. Oh, I was about to say something, but
Oh, the Rise of the Skywalkers. I
yes.
haven't seen it. I'm just sort of like nobody said like, oh, you should see it. So
Uh,
I'm not. Well, I might watch it eventually, but
I would suggest not doing that. Save yourself.
yeah.
Like,
See, they should have just stopped.
I mean, if you're the person who has that idle curiosity, if you have to look at like a
Yeah,
traffic accident because ooh maybe you
yeah,
get to see something like horrible mangled person, then
yeah.
watch the last Star Wars movie. But if you're a
Okay.
person who thinks to yourself, I have good impressions of Star Wars,
Yeah.
then for the love of God, save yourself.
Uh-huh. I
Yeah,
think it's already, my opinion's already been marred. Uh,
yeah.
what they needed to do was like they did with the Matrix movies, where they just made the first two and then they stopped because they knew they could never deliver.
Oh,
Like they could
oh.
have made a third Matrix movie, but they were like, you know what? We've just made too much of a promise. We've made this. We've added a twist that couldn't possibly be explained in a satisfying way. So we're just gonna
Well,
stop
no, but
here.
they had to have that weird cave orgy thing.
I don't know what you're talking about. That sounds like a fever dream.
Yeah, I mean, thank God that they didn't make a second or third Matrix movie. Ugh.
Yeah.
As it
Anyway,
turns out, it's
is it
very
time
easy
for
to ruin
math?
a good thing.
It is easy to ruin good things. This is why I only create bad things. Very hard to ruin them. They're already bad.
I, yeah,
Yeah.
yeah.
Hmm. So is it time? Is it time for math?
1 minute.
What's going on in the class now? Is how many more exam? Are you? This is like a homework class, homeworky class, right?
Yeah, more or less.
Yeah.
Yeah,
Okay.
homework and exams and then that kind of thing.
Are you gonna get to like the big O's?
Um, well, I, I was thinking of doing a little bit of probability, which I'm going to
Yeah.
start today. And I was thinking
Yeah.
of doing a little bit of graph theory.
Ooh.
And then I was going to do some big O.
Ooh, that's exciting.
Yeah, I mean, I figure it's useful, right?
Yeah. I hope everyone gets very hyped about the the big O's and the graphs and
Really
whatever.
better.
They better. They can finally speak with some level of authority about how efficient their code is.
Or how big the O is.
I wouldn't repeat that sans context.
Yeah, exactly.
Hmm.
I said that without thinking, and now I think about it a little bit. I'm like, oh, I could have said that. Yes.
Uh,
So I think half of our chat is just going to be people going, ooh.
big ooh. Let's get the big ooh.
All right.
All right.
Looks like
We're
it's
gonna go.
about time.
It's about time.
That's
So
right.
I'm here today. I'm gonna ask questions and generally
Cause
banter
havoc.
obnoxious. Yeah.
Cry havoc,
But
and let slip the dogs of war.
yep, gotta let those dogs of war slip.
Yeah, that's right.
What is that from originally?
Shakespeare.
That's right. No, but which one?
Oh,
Is that?
I wanted to say Henry the Fifth.
Yeah, it's. I don't think it's Henry VIII.
No, Henry the Fifth is the one at Agincourt.
Yeah.
You know, um, Cry havoc.
Because crying havoc is when you're like, I'm gonna pillage y'all,
Yeah, it's
right?
Henry. It's Henry the Fifth.
Yeah. But crying havoc is like, oh, it's pillage time.
More or less, yeah.
And then you let slip your dogs of war. You release the hounds. It's a very fancy way of saying
I wanted to
release.
do It's like, yes, Smithers, release the hounds.
Yes. There's dogs with bees in their mouth, and every time they bark, they shoot bees. Oh, the Simpsons. Now, oh, it's our pod. Yeah, this is the first episode of our incredibly lame podcast
Well,
where Eric explains binomial theorem to me because I've already forgotten.
I doubt that. Or have you? Are you going to
What, the
learn something?
binomial theorem? I know
Whoops.
that there's a p involved, and there's some.
Interesting. Tell me more about this theorem.
Okay, so there's a p
So,
involved,
okay.
and then
There's a P
And then
involved.
there's like an N. The binomial theorem's about a certain amount of trials, right?
That's the binomial distribution.
Oh, crap. Well, okay, but the binomial theorem doesn't have anything to do with the binomial
Oh,
distribution?
in fact, they are very related.
Okay, that's what I thought. Oh, gosh. Oh, gosh.
So
Okay,
P is
so there's like,
involved.
there's a
Okay.
bunch of there's a bunch of trials of probability
Bunch of
P.
trials. Yes.
Is that
Yes.
right? Am I
Yeah,
right?
yeah. If we're describing the binomial distribution.
Oh gosh. Okay. Well, and then the binomial theorem states something about the probability, the expected value of those trials, some n trials, and then
Just the
there's like an
probability
equation.
of those trials. You can also say what the expected value of the trials is, but we'll get to that.
Okay.
Oh, yeah.
Okay.
Okay.
So the binomial theorem is a way of describing the binomial distribution in a discrete manner.
I suppose you can say that. Let's look at it.
Okay, let's do it. You go. I'm gonna sit and ask you questions later.
All right. Hello,
Go,
everyone.
go, go.
Uh-oh. Is he muted yet? Yeah, I think he's gone. So, the good news is it doesn't matter. So, okay. Let's talk about the binomial theorem. This theorem is actually the binomial theorem. So, what does the binomial theorem say? Basically, it says if you pick any two real numbers and let n be a natural number, then this crazy formula is true. So, what does this formula say? What this formula says is that x plus y squared is, for instance, equal to 2 choose 0 times x squared plus 2 choose 1 times xy plus 2 choose 2 times y squared. And if you compute these numbers, yeah, I can turn up my mic a little bit. I can just move it closer, maybe even. Okay.
That's much better. You're much throatier.
Oh, thank you.
Yeah.
I'm pleased to hear it.
Yeah, good.
Okay, and let's do another example. So, incidentally, 2 choose 0 is 1, so this is x squared plus 2xy plus y squared. Let's look at x plus y cubed. Whoops. So that is equal to 3 choose 0 times x squared cubed plus 3 choose 1 times x squared y plus 3 choose 2 times xy squared plus 3 choose 3 times y cubed. And so if you compute these numbers, so as it turns out 3 choose 1 is 3. 3 choose 2 is also 3. 3 choose 0 is 1. And 3 choose 3 is 1. So what you're going to end up with is x cubed plus 3x squared y plus 3x y squared plus y cubed. So what's happening here is we see that as the power of x goes up, so as I is incrementing, we have n minus I, which is decrementing. So so whatever I you pick for this term, oh, I guess this should actually be I. There we go, fixed. So whatever I you pick, you get a coefficient of n choose I out in front, times x to the I power times y to the n minus I power. Well, Pascal's triangle is actually just involving coefficients. So actually your homework problem that had you deal with the fact that n choose k plus n choose k minus 1 is equal to n plus 1 choose k. This combinatorial identity is actually Pascal's triangle. And I've been meaning to draw out Pascal's triangle, but I just haven't remembered to do it. That is not how you spell triangle. I got too excited with the L and the E. There we are. Okay. So let's go back here for a little bit. And just let's talk about the proof of this thing before we move on.
Can I ask a question?
I suppose.
Why do we care about this? Are we going to use it for probabilities?
No, never. I mean,
Oh, okay.
yeah,
It's just
this is a completely irrelevant theorem that has no application in the rest of mathematics. In fact, I don't think that there's been a single research application of the binomial theorem.
I can't tell if you're kidding me or not.
Of course, I'm kidding you.
So,
okay. So let's prove the binomial theorem using a combinatorial argument. So here's the proof of the binomial theorem. I think this theorem is fun. So let's look at x plus y to the nth power. And for instance, let's just write out x plus y cubed as x plus y times x plus y times x plus y. So I'm going to do the same thing except with n. So I'm going to say, I'm going to say this, x plus y, x plus y, x plus y, bunch of dots, x plus y. And so let's see if I can do a good job. Ooh, I did. All right. So that's not a subtraction, that's just a bunch of dots. Okay, so there's n of these terms, n of these x plus y terms. And so now I'm going to ask a question. How many ways can we choose out of these n terms, k of them to be x? And then the rest are going to be y. Right? So this is the same as the light switch problem, which is you have n light switches. The number of ways to flip n light switches on or off is n choose k. Nice. So what that means is that there are n choose k ways to go amongst these terms and to pick, for instance, say this x, and this x, and this x, and some of the other x's in here maybe, and to pick the rest of them as y's. And then what you do is you multiply together this x times those x's times this x, right? And so if you want exactly k x's, then you're going to get x times x times x dot 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 x. You're going to get that k times. Well, that's not all we have to do though, right? Because if there's k light switches that are on, then we need the other light switches to be off. So instead of picking the x's, we have to pick the y's. And so in this case, we're going to have y times y times y times y, a bunch of those. How many of them are there? Well, there are n terms total. And so if there's n terms total, how many of these can possibly be y? And the answer is going to be, maybe I'll pause for a second and see if people start spamming the chat with it.
Can I ask a question while we pause?
Oh, sure.
So we have n term. We know there's going to be n terms because there's like n things getting multiplied together.
That's right.
And the x, because it's the light switch, x means like it could mean light switches on.
Yes.
And y means light switches off.
That is what it means currently.
And so x to the n would mean all the light switches are on, and x to the n minus 1 times y would be all of them are on and 1.
Yes.
Cool. I dig it. Awesome.
And in that case, where all of them but one are on, right, you had n choices of which one to turn off, right, Ben?
Yes.
And if you had n choices, then you would ask yourself, what is the combinatorial term n choose 1? As it turns out, that is n, right? So that's verified. That's, you know, an example of one term of the binomial theorem. Okay.
Nice.
So, good. people say n minus k, I agree. So, not only do you know it's n minus k because the theorem said so, but you know it's n minus k because there's n minus k light switches that are left off. So each term, right, is n choose k, x to the k, y to the n minus k. And I know I changed from I to k, but the variable you sum over doesn't matter. And so then the combinatorial argument would say, okay, well, but we don't know what k is, right? So k can be anything. Between 0 and n. So the combinatorial thing says sum, because k can be anything, you sum over all the possibilities. K equals 0 to n of n choose k, x to the k, y to the n minus k. So we've just proven, using combinatorial arguments, the binomial theorem. Isn't it beautiful? Yeah, k is less than or equal to n, right? So all right.
I don't know if it's beautiful so much as adorable.
No, it's definitely beautiful.
Oh, it's beautiful. Okay, all right. You're the
all right
guy.
So there's an inductive proof on it, right? I wrote proof, induction on n. I don't know about this one. It's gross. But actually, the fun, maybe I'll take that back. I take that back. What it is it's hiding this under a bunch of symbols and extra stuff. So the inductive argument is actually, I would think, less illustrative of the point. If you were in some kind of algebra class, they might make you do an induction proof of this. Basically, the point is you assume it's true for n, and then you multiply by another x plus y, and you see what happens. But let me promise you that it is an uninteresting proof, whereas the other one was inherently interesting. Okay, let's do something with this, right? Let's apply the binomial theorem a bunch of times, because that's what we do in math. First we prove a thing, and then we use it until we're bored of it. So this is a great identity. It doesn't look like it should be true. Or if it is true, it looks like the proof might be really hard. And so the nice thing about this fact is that all you have to do is realize, and this is a standard trick, is you look at terms in expansions. And so I'm going to make an argument to you. I'm going to say, crap, I keep hitting a button that stops me from. Zoom in a little. Maybe. I guess so. So, it's not exactly a geometric expansion, but it's something close. So what I'm going to do is I'm going to write two things down, and I'm going to tell you that they're the same. And you're going to say to me, obviously they're the same. Right? 1 plus x to the n times 1 plus x to the n is 1 plus x to the 2n power. And you think to yourself, wait a second. Isn't that the most obvious thing in the universe? I mean, if you believe in the power rules, yes, because you have two bases that are the same, and so that means you add the two powers, and so, you know, there ain't much there. Okay. Well, if you believe that, then, then what we're going to do is we're going to look at the x to the n term in both expansions. So let's talk about what the x to the n term is in both expansions. So in this one, we can just write it down, because the binomial theorem says that this thing is equal to the sum of 2n choose k, x to the k. And technically, it's 1 to the n minus k, right? And so that's why we can kind of drop this term, so you just ignore this. And of course, k starts at 0 and goes up to 2n. So if we're looking at the x to the n term, then what we get to do is we get to just pull out, just only pay attention to the x to the n term in this expansion. So here we plug in n, and we get 2n choose n, x to the n. And then we're going to have a big equal sign. And now the question is, what goes on the other side here, right? And the answer is, we're going to have to expand this product. So this is equal to the sum of n choose I, x to the I. And this one is equal to the sum of, say, n choose j, x to the j. So this is where it gets a little bit involved, but I think it's still good. So what I'm going to do is I'm going to try to figure out what happens. So what happens in the case of, say, 1 plus x squared? Oh, I'm sorry, that's not right. 1 plus 2x plus x squared, 1 plus 2x plus x squared, right? Let's just say that n is equal to 2 and do an example. So if we care about the middle terms here, then we would end up multiplying so both of these are based on the binomial theorem, right? This is x plus y, or really I guess you can say y plus x to the power n, which is how you get these two terms, right? You got this one from the binomial theorem, you get this from the binomial theorem, you get all of these from the binomial theorem. So if n is equal to 2, for instance, then basically what we end up having to do here is we want to look for the x squared term. Yeah, exactly. So we're ignoring the 1 to the n minus k because 1 to the, basically 1 to the anything is just 1, right? So if we're looking at the x squared term, we would get a 4x squared, but that's not all we get, right? Because we also get a 1 times x squared, and we get an x squared times 1. And so that's the thing that you have to see here, is that what ends up happening is, as the I power increases, the j power is going to decrease to keep us at n. So for instance, whatever I is, so whatever term we have, so we just have some term here times x to the I, we're going to have some other term, some like combinatorial term, times x to the n minus I. And that's going to keep us at the n term. And so we basically just have to consider what that is. And so here, what we're going to do, and so for instance here, we're going to get an x squared. So we get an x squared plus, and then here we get an, that's a 1 there. We get another x squared. And so I guess the other thing is like, okay, so this becomes 6x squared. And so the question is 4 choose 2 equal to 6? And the answer is yes. So basically this is equal to the same term as you would get over here on this side. So what I'm going to do is I'm going to write it out like this. So this is specifically the nth degree term. The reason why I'm ignoring all the other terms, I'm only taking those terms that add up to a power of n. So basically x to the n is something where you have x to the I, and then you have x to the n minus I is equal to j. Any other term produces a power that's either too big or too small. So if you look at this term here, then you'll actually see, we have to examine it. Let's put it on a new page. We have the sum of n choose I the sum of n choose n minus I. So x to the squared was just an example. We're really just looking at the x to the n term. So as it turns out, we're like 95% there. The only thing we have to do is, and I think I proved this in a different lecture, n choose I is equal to n choose n minus I. And so the question is, why is this the case? Let's go over that again. This is an important fact. So even if you don't completely follow this whole thing, this is probably one of the more important facts from this proof. And so the question is, why is it the same to pick out of a set of n things to choose I things as it is to choose n minus I things? And you can do the proof two ways. You can either say, well, it's n factorial over I factorial n minus I factorial. And this thing is equal to n factorial over n minus I factorial. And then here we're going to get n minus I factorial. And then once you do the cancellation, you'll see that this is I factorial. That's the algebra, right? But the combinatorial proof is actually even easier, because the combinatorial proof just says, hey, wait, if I pick out of a bag of n things, if I choose I things, that's the same thing as picking out of a bag of n things the rest of the stuff and discarding it. So n minus I is like the rest. And so you can either say, well, I'm choosing all the things I'm going to throw away, or I'm choosing all the things I'm going to keep. And that has to be the same number of ways to pick it both ways. And as it turns out, that is true. So basically, those are the two arguments for why n choose I is the same thing as n choose n minus I. And so if we just rewrite this sum, whoops, that's a terrible summation. That's better. We get n choose I times n choose I, so n choose I squared. All multiplied by x to the n. And so then what we have to do is we basically have to go back to our proof and remember what the heck we were doing. And so what we were doing is trying to prove that this thing was equal to this thing. But as it turns out, we've just done that because the x to the n term is sitting there, and we have n choose I squared. And that's what we got from the previous slide. So this is a really nice little argument. It just shows you how powerful the binomial theorem is, because this little fact here doesn't look easy, right? But as it turns out, it's doable with the binomial theorem.
Hey, can I ask a question?
I suppose.
How did you get 1 plus x? Is that just like a result of thinking?
You mean like right here, this 1 plus x business here?
The where you started.
Like right at the 1 plus x to the n, 1 plus x to the n?
Yeah.
I mean, that's total magic, right? Comes out of nowhere. What?
Okay, so that's the magic. That's sort of
I mean, so in a lot of mathematical proofs, right? Like you sit there for 2-3 hours thinking about what you're about to do, and then you have a realization. Well, if you had this realization here that 1 plus x to the n, right, times 1 plus x to the n was equal to 1 plus x to the 2n,
yeah,
then you're like 80% of the way done with the proof. Now, the thing is that, it takes, for normal humans, it takes hours to come up with this stuff, or alternatively, you can have learned it in the past and just know it, right? Those are the two ways to know it. So this is not something that I expect people to come up with on exams or something like this until I teach maybe generating functions.
Okay. I mean, because you can also assume if I'm supposed to apply the binomial theorem and there's no y here, that maybe. Yeah. So that's a pretty common thing. So let's do some easier examples. Yay.
So here's an easier example where, in fact, y is equal to 1 again. So I just want you to tell me what this number is. Right? This is, you can simplify this basically. And we're going to simplify it using the binomial theorem. And so the secret is, well, you see this n choose k here, so you're like, okay, and then we have a 5 to the k, and then you're going to do the secret 1 to the n minus k business, right? At that point, we basically have the answer, because we know that x plus y, or 5 plus 1 to the n. And that's it. So, you know, if you expand it this way, you would say, well, if 5 is equal to x and this is equal to y, then this is equal to the sum, you know, of n choose k, x, which is 5 to the k, times y, which is 1 to the n minus k. Then, of course, you just get rid of that. All right. So this is something that I definitely could expect on a test, homework, quiz type thing.
That's crazy.
You like it?
That was fast. I like sneezed and the proof was over.
Well, I mean, there's not much to it, right?
Yeah.
In fact, it is 6 to the n, yes. All right, let's do it again. Look at this one. So you see this, and you think to yourself, there's a 2r power here. Well, that's weird. How can I deal with that? So in this case, looking at the original binomial theorem, x equal to 5, y is equal to 1. Absolutely correct, yes. So this is another thing where we're going to assign 1 to the n minus r, because I guess r is the variable in this case. Who cares? Doesn't matter what you're summing over as long as it's consistent. So the secret here is that x to the 2r is really equal to just x squared to the power r, right? So when you're dealing with some of these things and you see like an extra power up here, consider what happens when you separate them. And so if you separate them, then you can see, like if I just make this variable the sum of like n choose r, say I make this variable equal to y now, and I just call this y to the r, where y is equal to x squared, and, you know, 1 to the n minus r if you really must, then you would say, okay, well, I know that this, as long as the summation is correct, is equal to 1 plus y to the power n. But as it turns out, this is also equal to 1 plus x squared to the power n. And we're done. So as it turns out, these are fun little simplifications. I might give some of these on a homework. Let's look at the next one, see what it is. There's all kinds of algebraic tricks that you can apply here. So here's one. And so the algebra that we have to do here, okay, I'll slow down a little bit. Let's look at this one. Let's do it again. Let's just say one more time. So remember that basically this is the binomial theorem. Let's write out the whole thing and choose k. Sure, x to the k, y to the n minus k. N equals 0. K equals 0 to n. So basically in this case, what we're going to do is we're going to pretend that in this formula at least, I guess what we're going to, so it's a little problematic because the variable here is called x. So maybe I'll call this variable x hat, just so that it's not the same thing as this x, right? This x is not the same. because I don't want to say something like, oh yes, x is equal to x squared, because then that's not true, right? So what I want to say is something, maybe I'll say, okay, y, for instance, in this formula is equal to x squared from this formula, and x from this formula is equal to 1 over here. And so that's how I get this 1 plus x squared here to the n. And if you're ever unsure, you can always expand it back out. You can always say to yourself, okay, well, this is equal to the sum of n choose k, x squared, and just be really precise about it. You can just be kind of pedantic about it and say, okay, x squared to the power k. And then I'm not going to write the ones. You know, maybe I will. I shouldn't. Okay. So, and then of course you can say, okay, well, you know, a to the b to the c, in this case, is equal to a to the bc. Therefore, x squared to the power n, or to the power k, is equal to x to the 2k. And so that's how you kind of go back and forth between these two versions of the same kind of formula. All right. No, this is all just the same problem. Okay, so let's do a new problem. So if we look at this one, let's take a look at this. Right, we have our m choose I, which basically when you see the m choose I here, this is a hint that maybe you can apply the binomial theorem. And so the thing is that you see this -1 to the I and you see this 1 over 2 to the I. And so you think to yourself, algebra? Is there some way to do some algebra to make this a little bit better? The answer is yes. And so what we're going to do is we're going to rewrite it like this. We'll rewrite m choose I equals, yeah, so basically what we're going to do is I'm going to put the -1 to the I over the 2 to the I. Yeah, exactly. So then what we're going to do is you recognize that if you have a to the x, or I don't know, I shouldn't use x, a to the lambda over b to the lambda equals a over b to the lambda. There. Now there's no repeat variables. Okay, so okay, so then what we're going to do here is technically, you know, if you're showing all your work, you have to rewrite the whole sum, which is annoying, but that's fine. It'll slow me down, so that's good. Whoops. -1 over 2 to the I. Cool. So now we can apply the binomial theorem to kind of get us back to where we started. And remember, we're going to have the same thing. It's a 1 to the m minus I. And so this thing by the binomial theorem must have come from, well, it must have come from -1/2 plus 1 to the power m, which is also known as 1/2 to the power m, which is also known as 1 over 2 to the n. So I think that, you know, this one shows just a different trick, right? The trick is that you, in this case, you want to combine these two terms into a single number that's both being taken to the I power, and then you can use that as a way to get yourself back here. Or at least get yourself back to something that's in the binomial form to apply the binomial theorem onto it. Okay. So x is equal to, yes. So yeah, x is, in this case, x is literally just equal to -1/2, and y is equal to 1. Yes. One more example before we leave this thing for good. So this actually is not such a bad example. It's a combination of a trick we've seen before, right? Here's a q to the 2i. So what do we do to a q to the 2i? We write it as q squared to the I. And p to the m minus I is fine. Fine how it is. No problem. So we're almost in the binomial theorem form. The only thing we have to do is a little bit of factorization here. So what we're going to do is then we just rewrite this thing, and we rewrite it as I is equal to 0 to m. M choose I. I'll just write the q first, because that's the I term, q squared to the power I, times p to the m minus I. Now, as it turns out, you assign this to y. You assign this to x. And there you go. So this has to be equal to q squared plus p. To the nth power. Can't forget that. Otherwise, that's kind of overkill. Okay. So, yeah, I think I'm going to give some examples maybe on homeworks about how to, or about more of these types of expansions. It's good to play around with these kinds of things. You may see one or two of these in algorithms. Okay. Let's see what the next slide is. I don't even remember. Okay. So here's, okay, why is it, let's see, go. Okay. Why is q squared? Let's see, I, x, and p. Well, just because the thing that is x, so in the original formula, you have two things. You have n choose k, you have an x to the k, and that power is going up, and you have a y to the n minus k, and that power is going down as k increases. And so here we have the equivalent things. This is the n minus k term here, and so that's why I call the p as y, and q squared is equal to x because it's the so the purpose is to apply the binomial theorem. Basically it's all just practice. I mean, really what we're doing is we're just doing some algebra games on complicated things to make them a bit simpler. So it's not something that's terribly conceptual. It's something that's more just algebraic and plug and chug. Okay.
But we're solving summations too. That's nice.
Well, yeah, I mean, summations are... But I mean, what is a summation really?
Scary.
I mean, it's an algebraic object that is there to be played around with, right? I mean, you just kind of mess around with them until there's something useful. I don't know. So, this is a blast from the past. blast from past. I wanted to go over this because there was a problem that I posed, and we kept getting towards it eventually, but never actually hitting it. And so here, you remember that if you ignore this part, the whole where part, and you just want all the solutions, the number of solutions to this equation where xi's are just bigger than or equal to 0, you remember the stars and bars technique, which just says that it's n plus r minus 1, choose r minus 1. And r is the number of variables, and n is equal to 35. It's just whatever the thing is on this side of the equation. So if you ignore all this, we're ignoring this, then we know that the number of solutions is 35 plus, I guess, 4 minus 1, choose 4 minus 1. So that is equal to 38, choose 3. And so let's see, what is that as a number?
Is that greater than 6?
It is slightly greater than 6.
Slightly greater than 6?
Yeah.
Greater than 12? Yeah, that's bigger than 6.
Yeah. So what was r again? R is the number of variables, right? Yeah. R is the number of variables. Well, okay. So now I'm going to erase, I think, everything here so that we have a clear view of the problem. And now we're going to ignore one thing. We're going to ignore that. And I taught you guys how to deal with this type of problem. Right? So what you can do is, if you know that 1 is less than or equal to x, then you can just say, well, if I subtract 1 from both sides, for instance, then I know that x minus 1, or x1 minus 1, for instance, here, just has to be bigger than or equal to 0 again. And so that will allow the theorem to just work, right? Stars and bars works when the variables are just bigger than or equal to 0. So what we can do is we can just subtract off these values. So that's the first thing that we're going to do. So here we can basically declare, for instance, y1 is equal to x1 minus 1. Y2 is equal to x2 minus 2. Y3, and I didn't make them too complicated. They were all just x3 minus 3, and finally y4 is equal to x4 minus 4. And so if we put all of this back into the original equation, what we're going to get is that if we subtract off a 1 here, a 2, a 3, and a 4, what we're going to get here, I guess actually that's just 10, so we're going to get 25 here. And so now we're dealing with the equation of y1 plus y2 plus y3 plus y4 equals 25. And so without this thing that I crossed out as hard as possible, we know the number of solutions to this is 25 plus 4 minus 1. Choose, I'll just say 3. So what is that? That's equal to 28 times 27 times 26 divided by 6. So as it turns out, that is equal to 3,276. So it's a little more than a third of the previous answers. So as it turns out, even just getting rid of a few of these possibilities really takes the number of solutions to this down pretty hard. Okay. So now let's get on to the important and kind of horrible thing that we have to do. So now we don't ignore this anymore. Now we can't ignore this. So the cool thing about this type of problem is that we actually have to think of it as two separate problems. The first problem is the thing we've just done. So this is the first half of the problem. The second half of the problem is how many of those previous solutions had x4 bigger than 12, right? Because these are all the solutions when we don't care if x4 gets as high as possible. I guess it can be as big as 25, and all the other ones. 3 comes from the fact that it's 4 minus 1. So how many of these previous solutions had x4 bigger than 12? And the answer is, well, all we have to do is calculate the number of solutions where x4, all the rest of them are the same, all else same, except that x4 is bigger than or equal to 13 now. And so given that fact, we can calculate the number of solutions to this new one. So instead of subtracting 4, so let's just redo the calculation. So basically now we're going to redefine y1 is equal to x1 minus 1, y2 equals x2 minus 2, y3 equals x3 minus 3. And then here, y4 is the different one. Is going to be x4 minus 13. So, and then that'll guarantee, if we subtract off 13, then that guarantees that x4 minus 13 is bigger than or equal to 0. And that's why we're setting that to y4. So what we're going to do is now, instead of subtracting off 4, we're going to subtract off the same thing. We're going to say 35 minus 1, minus 2, minus 3, but then in this case, we're going to subtract off 13. So 1, 2, and 3 is 6, 13 is 19. So 35 minus 19 is 16 total. And so now 16 is going to be equal to y1 plus y2 plus y3 plus, and hopefully I can get a y4 in here. Cool. So the question is, how many possible solutions are there to this thing? Well, that's a 16 plus 3, choose 3. So that's a 19, choose 3. Well, what is that? So 19, choose 3 is 969. Yep, and so in the end, the total answer is, as you just said, 28, choose 3 minus 19, choose 3. And so whatever that is, I guess, just subtract off 3276. That word is all, and it's all else are the same, not some. And so the reason I just said all else are the same, so I could avoid writing 1 is less than or equal to x1, 2 is less than or equal to x2, 3 is less than or equal to x3. If I had to write all of those again, I would have probably run out of space here, so I didn't. Okay. So this is kind of a this is a hard problem, I would say. This is actually a simplification of the problem that I was suggesting that we do earlier before I realized that that problem required stars and bars. And so that problem had upper bounds for all the variables. When it has upper bounds for all the variables, you actually need to use the inclusion-exclusion principle. And basically, you have to calculate like 10 of these and then add and subtract very carefully amongst them, right? Because, you know, for instance, like n of, you know, A union B union C equals blah, right?
Well, what would happen if you just added one more bound?
If you add one more upper bound, like if you say that this is less than or equal to 8,
Yeah.
so yeah, so what you have to do is you have to calculate the number of solutions where this thing is bigger than 12, which we did here, and then you have to calculate the number of solutions where this thing is bigger than 8, and you do it somewhere else, and then you have to calculate the number of solutions where both this thing is bigger than 8 and this thing is bigger than 12, because the thing is that sometimes this might be bigger than 12 and this might be bigger than 8, so you'll actually have an overlap in the set of solutions, and so you have to cancel out the duplicates.
Oh, you have to add the intersection back in.
Actually, you have to. You're right. You do have to, but it's a subtraction. But that's not the point. The point is, yes, you have to include, exclude. You have to add and subtract. Oh no, you're right. I think actually, I'm sorry. You are right. It is addition. You do have to add the intersection back in.
Yeah.
But yeah, because it's
taking them out one extra time.
Yeah, you're taking out. Yeah, I had the signs flipped because in the regular inclusion exclusion you include the singletons and you subtract the intersections. But anyway, but yes, so yeah, if you have lower bounds are fine, right? Because lower bounds you just use the standard trick where you shift the variables, right? That's what you do for lower bounds. You shift them. And so we dealt with lower bounds in a previous class, and then we dealt with lower bounds right here. Like if this wasn't here, then this would just be the answer to this whole problem. And so basically dealing with lower bounds is easy. Dealing with upper bounds is kind of awful because it can degenerate. Like the more variables you have, it's not quite exponential. Actually, it is a little bit exponential in the number of terms you have to calculate. So that's why I chose to do one upper bound, where I had to do one calculation rather than... Because if you do two upper bounds, then you have to do 4 calculations. And if you do 3 upper bounds, then I think you have to do 8 calculations. If you did 4 upper bounds, you have to do 16 calculations.
Yeah, that sounds sweaty. And that sounds like too much stuff.
Well, it's too much for this slide, at least.
Yeah.
This looks like a job for MATLAB. You know, it probably is, yeah. Or a whole bunch of for loops, right? Like, literally, since the numbers are small, right? Like, a few thousand, you could just have a for loop go through all that stuff and get you an answer within a reasonable length of time. You know, maybe a few seconds at most. But if you were trying to do something where the this number was like 35 million, then obviously you would just have to use the formulas because that would be the faster way to do it. Okay. I mean, I try my best to do both of those things. Okay. So, all right. So let's talk a little bit about probability. So this lecture has been pretty algebraic so far. So maybe we'll take it easy for the rest of the lecture. So let's talk about what a probability distribution is. A probability distribution is a sample space. So a sample space is a term that they use in probability. Really, it's a set. In set theory, you might call it a universe. Whoa. That fought me pretty hard. So in set theory, you might call this a universe, along with a function p. So basically, you have a set and you have a function. And so basically, there's some rules. The rules are that all probabilities have to be between 0 and 1. So that's really 0% up to 100%. So if you pick any event, now event is another term that we have to use in probability, but the good news is that an event is just a subset. There's nothing special about events except that it's just the word that they use in statistics rather than subset. Okay. And so basically we would say all of the events, so all of the subsets have to have a probability that's between 0 and 1. That means that we can't have a probability of something. For instance, there's no probability of A, which is like 235%. And the reason for this is that so you can have numbers that are above 100%. So there's nothing wrong with having a number that's above 100%. But there is something wrong with having a probability that's bigger than 100%. So let me explain the difference. So for instance, in fact, it does have a correlation because this is the double union formula. You know? And so, except instead of having just the number of things, now we just have the probabilities of those things, right? As it turns out, that is not an accident. So, okay. So when people say that like a percentage of something is, yeah, I guess it does look a little bit like the integral. The integral of formulas is equal to a textbook, I guess. So, okay. So the thing to talk about here is that before I move on, I just want to say that there are percentages that are higher than 100%. So you can always say that like a power plant is operating at 110% of, you know, it's like designed output, which means that it's producing more power. It's producing 1.1 times the expected power, or the designed. Right, so that is 110%, right? If someone says, you know, give 110%, I mean, technically, if you know, somehow you can give more than your designed quota of power, then that is what you can do. On the other hand, a probability of 110%, if this is the probability of some event, this is nonsense. And the reason why it's nonsense is because if something's 100% likely, then it's, you know, certain to happen. So if something is 110% likely, the joke I would always make is that, you know, it's 100% likely in this universe, and then there has to be another universe where it's also 10% likely. But again, that's nonsense. So, so I would say avoid, if you ever find yourself with a probability that's outside of this range, you've done something wrong. And then let's go on to this other stuff. The probability of the null set is 0, and the probability of the entire sample space is 100%. So basically all this is, I mean, this axiom is just kind of boilerplate stuff. This is stuff that you should expect if this makes any sense to describe probability. The probability of nothing happening should be 0, and the probability of literally any of the possible events happening should be 1.
So some event must always happen.
Yeah, some element in the sample space must always come up. Otherwise, the sample space doesn't describe the entire sample space. So it's not a sample space. Okay. Yeah, okay. I mean, that's kind of the idea here.
So you throw the die, there always has to be a face that comes up. More of it.
Yeah, basically. So like if you said like our events are, if we're dealing with coin tosses and we say, you know, our sample space is heads, right? Then that's garbage. Because then there are events that can happen that are outside of the sample space, right? You would have to make your sample space like heads, tails in order for it to be a meaningful sample space for that probability event, right? And same thing for like rolling a die. You know, you'd have to say 1, 2, 3, 4, 5, 6 if it's, you know, a six-sided die. Is the sample space for rolling a six-sided die. If you left any of these numbers out, then you would have events that could happen that are outside. Yeah, actually, I did. Ooh, I wasn't even touching the board at that time. Okay. Yeah. So I. Oh, interesting. If I touch my. Oh, that's weird. Okay. So. Yeah. So this is the null set. Okay, and so then the last axiom for probability distribution is something that you generally don't really have to verify, hopefully. And that's basically, we're just assuming. That's a good question. How do you determine a sample space for more complex scenarios? So the answer is generally that, like, you got to make sure that you have all the possible events. So we'll do some examples maybe next time of more complicated sample spaces. Like this time, our sample spaces are going to be pretty simple, but you're right that it's important to ensure that that all the events are stuck in somehow. A lot of the time, you can kind of be sure if you do some kind of combinatorial argument, you count up the number of things in the sample space and you determine that's the right number of events. Okay. So yeah, the last axiom, axiom 3, is just kind of like saying probability has to play nicely with set theory, and it has to play nicely enough to where the double union formula holds. If the double union formula didn't hold in set theory, or I mean probability, then we would have issues because we're using sets for everything, and so we expect that like these sets will be able to translate directly into probabilities somehow. Okay, so those are the 3 axioms. The good news is because this class has gone online, you are not going to be tested on memorizing these axioms. Because memorization is pointless in take-home tests. But you should know these 3 axioms. You should be familiar enough with them. For instance, if I asked you to verify that something was a probability distribution, you would be able to do it. Basically, verifying it's a probability distribution, these things are usually automatic. Normally, you have to verify that all the events add up to 1, and then you just have to check this. Generally, this comes for free. Generally. This part is free. Okay, so let's do some calculations. So let's suppose that the probability of A is 0.6, so that's like 60%, right? The probability of B complement is 40%, so the probability of B is going to be, and so the reason why we know this, so the probability of B is going to be 1 minus the probability of B complement. And that's because we know that the number of things in B is equal to the number of things in the universe minus the number of things. I'm sorry, the number of things, yeah, in B complement. And so the good news is that this formula holds in probability as well. So you can just subtract. Basically, this thing is just equal to, instead of being n of u, it's just the probability of the entire sample space. So it's the probability of S. Okay. And also we're told that A intersection B is 0.2. So we want to find P of A union B. So let's do it. Probability of A union B is equal to the probability of A plus the probability of B minus the probability of A intersection B. So this is equal to 0.6 plus 0.6 minus 0.2, which is equal to 1. So what does that tell us, right? So this tells us that when you union A and B together, this must be the whole sample space.
So does that mean that either A, B, or both of them are always going to happen?
Yes.
Cool.
Yeah. Well, because, so, I mean, I was just thinking technically you could include a bunch of probability 0 elements in your sample space, but who cares? Because those things will never happen, right? So technically this is not actually quite true, but it is true if you ignore elements of probability 0. So elements that have literally 0 probability, if you assume that you just don't have any, then it's true.
So what if A union B had a probability of 0.1? Is that like an aberration? Can that like just not happen? Because
so if you mean you made like say 0.8, and then you said probability of A union B is just 0.8, let's just assign it, and then you say like, okay, 0.6 plus 0.6 minus 0.2, like this, is that what you're saying?
No, I'm saying like in the problem above,
Yeah.
if they said the probability of A intersect B
Yeah.
is 0.1, then you would get a probability
Yes.
over 1.
Yes.
So that, what happens?
Well, that tells you
That's
that
just a bad. Is that just a bad problem?
well, so right, so that it's either a bad problem or you were promised a probability distribution that isn't true, right? I told you that this set thing and this probability function is actually a probability distribution as defined on the previous slide, and it's just not, because you just ended up with a probability higher than 100%. Right?
So we would just point back at the person who gave us this problem.
Yeah, more or less. Yeah, so
yeah, okay.
B complement includes the overlap of A and B, right? The answer is no. B complement includes the part of A that's not in B, right? So if you draw the Venn diagram and you look at A and you look at B, then B complement is this part and the outside. Yeah, it would just be a bad, I mean, you could say it's a bad problem, or you could say it's an ill-defined probability distribution, or whatever. I mean, there's a whole bunch of things you can say about it other than it has an answer. That's the one thing you can't say.
Okay.
Okay. So let's do it again. Look at this one. And of course, there should be slight terror when you see this symbol. But whatever. Probability of U is going to be equal to 0.7. And the probability of V is 0.6. So find the probability of U union V. So the probability, let's just write out the double union formula. The probability of U union V is equal to the probability of U, which we know, plus the probability of V, minus the probability of U intersection V, which we don't know. So we don't know this one, and we don't know this one. So which one might we be able to figure out? So the answer is, what the heck is this? Right? It's the probability of U complement union V complement is 0.4. Well, okay, fine. 0.4 is a number. I don't care. The real question is what can I do with this thing? And the answer is what I'm allowed to do with it is I am going to recognize that U complement union V complement is equal to yes, in fact.
Is it intersect UV complement? Oh,
yeah. Someone beat you to it, Ben.
I mean, I didn't want to interrupt, but they are
No,
also
it was great.
common.
Yeah. So as it turns out, this is De Morgan's laws. Well, I guess De Morgan is not spelled with a B. So De Morgan's laws gives you this, and you know that the probability of U intersect V quantity complement is equal to 0.4. Therefore, the probability of just U intersection V is 1 minus 0.4, which is 0.6. Now, this problem also has an interesting kind of edge case. Because now that we know that this is 0.6, what else do we know? We know that U intersection V is equal to V this time. Right? This is certainly not guaranteed. Right? Not guaranteed. But it's just true this time.
Does that mean V is a subset of U?
In fact, that is... if you want to torture them, yes. That was an...
I didn't want to torture them, no!
Okay, no, because that was literally number 2 on their first exam, was to prove that if A intersection B was equal to A, then A is a subset of B.
Oh, is that a proof by Venn diagram?
Well, you can do it by Venn diagram. There's a bunch of ways to do it.
Cool.
So yeah, and then let's see. So the U complement and V completely irrelevant for the problem. No. So we needed all of this work was just to give us this part here. These two things here we still need because the last thing we want to compute is this answer. And so we still needed to know what P of V was, and we needed to know what P of U was, so that we could, once we figured this out, then we could say that P of U union V was equal to 0.7. But as I say, the reason why these numbers are repeating is just because the problem is constructed in a kind of weird way. It's not necessarily because there's anything magical about these numbers or that they're gonna always do that. Okay. Let's see what the next problem is. Nope. Definitely not. Nope, Reno. Okay. So that's where the class ends, because so this problem is a binomial distribution problem.
This is what I was rambling about, right?
Yeah. So finally we get to the interesting part, and class is over. But don't worry, just join me on Wednesday, and we'll start up right here. Right
and
here.
We're shooting arrows?
Yeah, we're gonna shoot arrows at the target. We have a target.
This problem has
and we're
everything.
shooting arrows, right? I guess.
Oh my gosh, it's got action. Is there will they won't they kind of thing? Is it about maybe the arrow and the target? It's like, oh, everybody's been wondering, is that arrow and the target, are they going to be, in an event together? Yeah.
I couldn't tell you, Ben. I in fact, I just blanked out the last 30 seconds of my life. So.
Oh, this is so exciting. I don't remember how to do this. I know some things.
So as it turns out, if you want K successes and N trials, it's N choose K. P to the K. Q to the n minus k. Doesn't look familiar at all, does it?
No, that seems I can't apply any of my past experiences to current ones, so
Yeah,
this
you
is
see,
confusing now.
I guess this thing is almost like an apple if we just kind of do this and then, like, a little
Oh, we
a
get an
gigantic
yeah,
stem. Yeah. So, yep. Okay. I didn't say when the next exam was, and I see a few people curious about it. I think I might have mentioned it in previous classes. I'm not sure if I have decided. Good question. When should the next exam be? I guess either maybe I'll release it on the 15th. You guys will have a week. But obviously that's not official until I'll tell you Wednesday. Okay. All right, everybody. It was fun, right? We got to do some binomial theorem proofs, which are like a lot of fun. And then
algebra.
Yeah, we did some algebra, and we had a visitor.
Yeah, hi.
What about if you still have to take the first one? So, yeah, I'm gonna write a makeup for you guys probably maybe tomorrow.
Oh yeah, makeups are such a mess now.
Yeah, I mean the makeups for the two unfortunates who still haven't taken it are gonna be take homes, obviously. So they're gonna be interesting exams. So, and
yeah.
The definition of interesting is not good.
No,
if I'm saying it.
Interesting can be good. Blue Jays are interesting, and
no. But if I'm saying it.
Oh, if you're saying.
Yeah, if I'm saying the word interesting, is it good or is it bad?
If it's interesting, it's probably bad.
Yeah, it's probably bad. Very good.
You're like, ooh, that large person with a knife is interesting.
Yeah, I would find that very interesting. It would take up all my attention.
Yeah, certainly would. Yeah, it would be a matter of great interest. We love guests.
All right. Well, I'm signing off, so all you guys can go and do whatever it is that you do when you're not calculating probabilities. Which I can't even conjecture a life beyond that. So I mean, really, in the end,
they do 202 projects probably.
Yeah, I mean, I have a dog.
Yeah, there's a dog. Can you dab on camera?
I certainly.
No.
If I get 200 subs, no. I think I would need more than that because if I get if I get every student subscribing, I'll dab.
No, don't do it.
But I'll do it once.
No.
And I'll be like one of those boomers who doesn't know what it means and just do it and not care.
No, don't do it. Or do it off. Or you could do it off camera, and that'll be.
All right, I'm signing off so that they can go, and then we can continue our conversation.
We're going to continue this.
Offline.
Yeah. Goodbye, nerds.
Bye, everyone. Hey, now, be nice.
Well, no, I mean that with love. Oh, you have your outro going? Oh.
Yeah, man. It's crazy.
I haven't sorted that out yet.
I can help you with that.
Yeah. Wait, was was it still playing our audio while?
Oh yeah, no, it's still playing it now.